Hi, Professor Barati here. I'd like to go over the theory of constraint problem in Chapter 4 to help you figure out how to calculate some of the questions on the problem. Also, there will be an extra credit problem that will on the exam that may help you get some extra credit. So I would give this a good look. And so let's talk about this problem. It's Austin Enterprises makes and sells 3 types of dress shirts. You have the basic, the classic, and the formal. Management is trying to determine the most profitable mix. Sales mix, demand, and use of manufacturing inputs follow. So, for a basic shirt, price is $38, for a classic is $70, and for formal is $200. The maximum demand in units for these shirts are respectively 18,000, 11,000, 28,000. The input requirement. It requires 0.7 yards of material to make a basic, 0.5 yards of material to make a classic, 0.8 yards of material to make a formal. Direct labor requires 0.9 hours for basic, 2 hours for classic, 8 hours for formal. Our variable costs are as follows. Materials are $18 per yard. Direct labor is $14 per yard. Factory overhead is $5 per direct labor hour. Marketing variable costs represent 10% of sales price. Annual fixed costs of manufacturing $50,000, marketing $7,500, administration $44,000. So you should automatically realize that given the way variable costs and fixed costs are identified, that you're going to be working with contribution margins. And so there'll probably likely be a contribution margin question of some sort or per unit. The company faces 2 limits. The volume of each type of shirt that it can sell, which is the annual demand given to us in units above, and 2, 35,500 direct labor hours per year caused by the plant layout. The 35,500 direct labor hours per year is the most direct labor hours we have for our factory. So it is a constraint. The second thing you must think of when you see this is you must ask yourself, this is a product mix problem. Therefore, we have to figure out the most profitable use of those direct labor hours. How to allocate the most direct labor hours to the most profitable product first. Then, if there are any direct labor hours available for the second most profitable product, we allocate to that. And down to the third product, if there are any hours available to produce the third product. So based on this problem, we're going to figure that out. Required. Assume the company can satisfy the annual demand. Calculate the contribution margin for each type of dress shirt using the table below. So let's calculate that. It's fairly easy. I've built a spreadsheet. Basically copies our basic, classic, formal. It copies the sales price per unit, the annual demand, the input, and then the variable costs and the fixed costs are here. So we're going to create a contribution margin statement for each shirt. So we know the sales price is $38. The demand is $18,000. Let's figure out our direct materials. It takes 0.7 yards to make one shirt. Therefore, it costs $18 per yard. Simply take the 0.7 times the $18 per yard to come up with your material costs per unit. Make some room here. Direct labor hours. It takes 0.9 yards to make one unit. The direct labor hour is $14 per hour. Therefore, take 0.9 yards times $14. Coincidentally, they're the same number, so let's just double check. 0.7 times 16 and 0.9 times 17. Overhead is $5 per direct labor hour. We know we have 0.9 hours, and let me just correct that from yards to hours. It takes 0.9 hours at $5 per direct labor. So just take 0.9 times 5. Variable overhead is $4.50 per unit. We know the marketing is 10% of sales price, so simply take the sales price and multiply that by 10%. So our total variable costs per unit is the sum of these. So let's calculate a little contribution margin. Our sales or revenue is simply the sales price times the demand. Our variable cost is simply our variable cost per unit times demand units. Our fixed cost is fixed. But they want a contribution margin. So the contribution margin doesn't include fixed costs. It's just sales minus variable costs. Let's do the same for the classic. Equals 0.5 times 18 equals 2 hours of direct labor times $14 per direct labor hour is a rate of $28. Equals 2 hours of direct labor times $5 per direct labor hour gives us the variable overhead. And this basically, this formula put an F4 there to lock that in. times the 38. And we'll copy that over. So that is $70 times 10%. So our variable cost per unit is $54. So our revenue is basically the $70 times 11,000 units. And our variable cost is going to be 11 times the 54 to get a contribution margin of 176,000. And finally, for formal, I'll do this quickly. Same thing. 0.8 yards times the $18 equals 8 hours times 14 equals 8 hours times 5. Oops. And then the overhead, we'll keep that formula in place. You get $20, which is basically 10% of 200. Copying this across. And our answer is 380,000 contribution margin. How much operating profit could the company earn if it were able to satisfy the annual demand? Which is A2. So basically, let's just total up our contribution margin. So we'll put total here. So our total contribution margin is 637. Our fixed cost, which we're going to put here, is given to us in the problem right here. Let me put that right on the right row. We'll link that. Operating profit is going to equal contribution margin minus fixed costs of 536,300. Compute the contribution margin for each shirt per constrained resource, direct labor hour. So what I've built here is basically the contribution margin per unit. I took the total contribution margin of 81,000 and divided it by the number of units, 18,000, to get a contribution margin per unit of $4.50. Or you could simply take in the $38 sale price and minus the $33.50 total variable unit. That would have given you the $4.50. Same here, I took the $176,000 in contribution margin, divided it by 11,000 to get the contribution margin per unit, which is $16, or you can simply take in the $70 and minus the 54. You could have taken 200 and minus the 186 to get a $13.60 contribution margin per unit. The constrained resource in the problem are the direct labor hours, and we know that it takes 0.9 direct labor hours to make one basic shirt, 2 hours to make a classic, and 8 hours to make 1 unit of formal shirt. To get the contribution per direct resource constraint, which is the direct labor, simply take the contribution margin per unit of $4.50 and divide it by the number of hours it takes to make one of these shirts, in this case 0.9. So for every direct labor hour, 0.9 it takes to make one basic shirt, it gives us $5 of contribution. For every 2 hours of direct labors it takes to make the classic, we get $8 of contribution from those 2 hours. And same with the formal. So your contribution per direct resource is $5, $8, and $1.70. Which of the 3 product lines makes the most profitable use of the constrained resource? Your answer is going to obviously be the highest on the constrained resource, which is $8. Understand the question. It says what is the most profitable use of the constrained direct labor? In this case, it is the classic. Don't go by the contribution margin per unit as your answer. The question didn't ask which product has the highest contribution margin. It asked which product makes the most profitable use of the constrained resource. In this case, it's the same, the classic. Given the information in the problem so far, and I'm reading right from the part C, given the information so far, what product mix do you recommend? You want to recommend a product mix of classic first and basic next, because they give you the most contribution margin per direct constrained resource. In this case, D1, they want us to calculate the contribution margin for each type of dress shirt based on the constrained resource. So to figure out the contribution margin for each type of dress shirt based on our constraint, the constrained resource in the problem tells us there are only 35,500 direct labor hours available to produce these 3 shirts or these number of units. What we have to do is allocate this 35,500 based on the most profitable mix of the contribution margin per direct resource, because the direct resource is what's driving the mix. So we start off with 35,500. So 1, look at the most profitable product with the highest contribution margin per direct resource first, which in this case is the classic at $8. Look at the input. It takes 2 hours to produce 1 unit of classic. So 2 hours to produce 1 unit. If we were to maximize the production of classic, we can produce 11,000 shirts. That gives us 22,000 hours available. Do we have enough hours in our resource bank, 22,000, to produce 11,000 units of Classic? Yes, we do, because we have 35,500. Therefore, we can produce all 11,000 units. That leaves us 13,500 direct labor hours available between basic and formal. So let's see if we can produce all $18,000 of basic. Simply take the 13,500 and divide it by the input of 0.9 hours to make one shirt. That'll give us the answer to the maximum number of units we can produce of basic, 15,000. Our max is 18, but our constraint limits us to 15,000 units. So we're going to take 13,500 off our balance, okay, for the basic. And that leaves us with 0 left, which means we have no hours to produce formal, which has a maximum demand of 28,000 at 8 hours. 1 hour to produce 28,000, 8 hours to produce one formal exceeds our constraint. So let's figure out the contribution margin based on our constraint right here. The contribution margin for basic is $4.50, and for Classic is 16. Number of units to produce based on the constraint. In this case is we could only produce 15,000 out of 18,000, and we could produce all 11,000 out of the Classic. So the contribution margin is $4.50 times 15,000. $1.76. So the contribution margin based on our constraint would be $167,500 and $176,000 for the Classic. Our total contribution margin based on these constraints will be $243,000 less our fixed costs of $101,000 gives us a new operating profit of $142,000. That's the profitable mix that we can conclude using the constraint. Part E says, suppose a company would expand its labor capacity by 17,000 more hours. So instead of 35,500, we add another 17,000. That gives us 52,500 to work with. However, the direct labor cost would increase from $14 to $17 per hour for all hours of direct labor. What additional products should Austin manufacture? So let's do this last piece. I'm going to copy over this. and put 52,500 in there. And I'm going to go to our input and say direct labor hour instead of $14 is $17. Notice this changed. So our contribution margin now is $38 minus $36.20, which is $1.80. And 70 minus 60 is 10. And 200 minus 210 is minus, because it takes a lot more hours. So at $17 per direct labor hour, 8 times 17, our direct labor hour is 136. That means our variable costs are higher than our sales. So once again, the most profitable product in our mix per constrained resource of direct labor hour will still be classic at 5. Next is basic, and I'm not sure we even want to make formal, but we'll see how the problem works out. So now the number of hours to produce input did not change, just the dollar amount. So if it takes 2 hours to make 1 unit of classic, that means we can produce all 11,000 units. Okay, so now 30,500 is available. So if we take 30,500 available, that means we can produce 33,888 or 89 units of basic. But we could only, maximum demand is 18,000. So in this case, we're going to produce all 18,000 units. The contribution now is 142,400. And the additional profit from the last one would be $5,400. We wouldn't produce formal because it loses money. And here is basically the summary of that. The operating profit now becomes $142,000. So if we calculate the contribution margin, operating profit is $142,000. So this concludes our basically constrained theory problem. And if you just follow the steps via the spreadsheet or come up with your own spreadsheet, just understand the theory behind it. Hopefully this helps you understand how to best allocate the resource. And in reality, most companies work with plenty of resources such as machine hours, labor hours, square footage, and so on. And it is used in practice, and it's a good algorithm to understand. Thanks for watching, and hope this helped.